All right, we're going to start section 11.4, which is the comparison tests. Now, it's actually two tests that we're going to talk about. We'll talk about just a regular comparison test in the section, and then also what's called the limit comparison test. Both are very important. So I'm going to start off with the regular comparison test. Suppose that we had the summation as n equals 1 to infinity of 1 over 2 to the n. Okay, that's a geometric series. And sets the sum as n equals 1 to infinity of 1/2 to the n. Now, in order to find out what it converges to, I need to make sure that I'm in the form a times r to the n minus 1 if I'm starting at n equals 1, and I am. So I'm going to factor out a 1/2. And I have the summation as n equals 1 to infinity of 1/2 times 1/2 to the n minus 1. So a is 1/2, r is also 1/2. A divided by 1 minus r is 1/2 divided by 1 minus 1/2. 1/2 divided by 1/2 is 1. Okay, so this is a convergent series. Now, what if I had the sum as n equals 1 to infinity of 1 divided by 2 to the n plus 1? Okay, well, these two series look very similar to each other, right? So because of that, I'm going to want to consider using the comparison test. By the way, a lot of these comparison tests are going to be where you're comparing a series to a geometric series or a p-series. Consider that. Consider that when you're figuring out what to compare it to. Okay, and you'll see me doing that for a lot of these problems. So now I know that this series converges. Okay, 1 over 2 to the n. What if I compare that with 1 over 2 to the n plus 1? I'm comparing the sequences to each other. Okay, so I'm going to lose the summation notation. Well, if I add 1 in the denominator here on the left, then the overall numbers on the left are going to be smaller than the ones on the right because the denominator is going to be a bigger number. And because the denominator is going to be a bigger number, again, the overall number on the left is going to be smaller than when compared to the one on the right. And this is true for all n greater than or equal to 1. Now be sure to write this down, the conditions on n. Sometimes this inequality that you'll set up here won't matter because the inequality will be true for all n, but sometimes it will matter. Okay, so sometimes it's not going to be true for all n, and I'll see students not write this part down. Okay, for what values of n the inequality is true or not. Okay, now if I take the summation of both sides, so the sum as n equals 1 to infinity of 1 over 2 to the n, that's 1. And I was comparing term by term with 1 over 2 to the n, 1 over 2 to the n plus 1, and term by term, those are all smaller numbers. Okay, so the grand total, when I add up all infinitely many of these numbers, is going to be some number that's less than 1. So this series would be convergent also. I don't know what it converges to, but I know it's convergent. Okay. So here's what the comparison test says. Let 0 be less than a sub n, which is less than or equal to b sub n. A sub n and b sub n are sequences for all n. Okay. Then item 1 here, if the summation as n equals 1 to infinity of b sub n converges, then that's going to imply that the summation as n equals 1 to infinity of a sub n converges because a sub n is smaller than b sub n. Right? So if I know that the sum as n equals 1 to infinity of b sub n converges, and I'm adding up a bunch of smaller terms, well, I know that the sum as n equals 1 to infinity of a sub n, that's also going to converge. Okay. Then item 2, if the sum as n equals 1 to infinity of a sub n diverges, then that's going to mean that the sum as n equals 1 to infinity of b sub n also diverges because you're going to be adding up a bunch of bigger numbers. Okay. And, if I add up, these numbers here with a sub n and it diverges, I get infinity, and I'm adding up, bigger numbers, well, I'm obviously going to get infinity. Okay. So these two tests are the comparison tests, okay? So let's take a look at some examples of where we're using that here. Suppose that we want to find the sum as n equals 1 to infinity of n squared minus 1 divided by 3n to the fourth plus 1. I want to know, does that series converge or diverge? Okay, well, I'm going to use the comparison test. And by the way, when you're trying to figure out what to compare it to, again, like many times you're going to be comparing the sequence part to something that's a geometric or p-series type thing. Okay, so consider that. Okay, so and by the way, it is common for us to leave off terms that we're adding or subtracting and just see which side is the bigger side after doing that. Okay, so I have the sequence n squared minus 1 divided by 3n to the fourth plus 1. Now, what if I did not have the minus 1 up top? Well, if I didn't have the minus 1 up top, then the right side is always going to be bigger than the left side, right? Because the left side, you're subtracting 1 in the numerator, so the left side is going to be smaller than the right side. Okay, and that's going to happen for all values of n that's bigger than 1. Now, what if I get rid of the plus 1 that I see in the denominator there? And I have n squared divided by 3n to the fourth. Well, the expression on the left, n squared divided by 3n to the fourth plus 1, that's always going to be smaller than the one on the right because you're adding 1 in the denominator on the left side. So the entire left side is going to be a smaller number than it would be compared to the one on the right if you're subtracting 1 in the denominator. Or excuse me, if you're adding 1 in the denominator there. Okay, the denominator is going to be a bigger number on the left. N squared divided by 3n to the fourth, that's the same as 1 over 3n squared. And the sum as n equals 1 to infinity of 1 over 3n squared, 1/3 is a constant, you can pull that in front of the sum. You have 1/3 times the sum as n equals 1 to infinity of 1 over n squared. That's a convergent p-series. Okay, so remember that you got 1 over n to the p. If p is some number that's bigger than 1, you're going to have a convergent p-series. If p is so positive, but it's less than or equal to 1, then it's divergent. Okay, so here p would be 2. Well, so this series is going to be convergent. Now, if I'm comparing term by term, you know, the original series to this p-series here, and I'm adding up everything in this p-series, and I get something that is a grand total that, is a finite number, is convergent. And over here, I'm adding up smaller numbers. Well, I'm still going to have something that converges. Okay, so the sum as n equals 1 to infinity of n squared minus 1 divided by 3n to the fourth plus 1, that converges. Okay, now you're comparing the sequences. I notice that I don't have any summation notation over here. Okay, I see sometimes where students get carried away with the summation signs and they're writing summation signs all over the place. Don't do that. Okay, know what it is you're writing down. Okay, so if I have a summation sign, that means I'm adding up all the terms. I'm not adding up anything over right here. All right, I'm just comparing term by term. What side's bigger? So is the left side bigger or the right side bigger? Right? Okay. Let's try this example next. So what if we had the sum as n equals 1 to infinity of n divided by 5n squared minus 4? Okay, well, I'm going to compare the sequence n divided by 5n squared minus 4 to, now I'm subtracting 4 here. What if I did not have the minus 4? What if I just had n divided by 5n squared? Then what side's bigger? Well, the left side is always going to be the bigger side if I'm subtracting 4 in the denominator. Because, so like if I let n be, 5, for example, excuse me, if I let n be 1, sorry. If n is 1, I have 1/5 on the right, and n is 1 over here, so 1 divided by 5 minus 4 is 1. 1 over 1 is 1. 1 is bigger than 1/5, right? And the left side is always going to be bigger than the right side. If I'm subtracting 4 in the denominator, then that means that the denominator on this side is going to be a bigger number than compared to the one right here. Okay, so the overall fraction on the right is going to be a smaller number. N divided by 5n squared, that's 1 over 5n. And this statement here would be true for all n that's greater than or equal to 1. Okay, now, again, here it matters. Like, so if I didn't say, you know, for all n greater than or equal to 1, then this statement is not true for all n. Okay, like if n is -1, which we're not using, we don't care about that, but if n is -1, you have -1/5 on the right, and you'll have -1 on the left. So you're saying -1 is bigger than -1/5. That's not true, right? And plus, n can't be 0 also, right? Because you can't divide by 0. Okay, so be sure to write down like for what values of n this comparison statement happens. Okay. Now the sum as n equals 1 to infinity of 1 over 5n. If I factor out a 1/5 from that, then I've got a p series, where p is 1, or a harmonic series. Okay, so the sum as n equals 1 to infinity of 1 over n, I know that's a divergent series. And I'm comparing, you know, things on the left with things on the right. And the things on the right, if I add up all infinitely many of these terms, I get infinity. Well, if I'm going to add up all infinitely many of these terms on the left, which are bigger numbers, I'm still going to get infinity. Okay, so the sum as n equals 1 to infinity of n divided by 5n squared minus 4, that diverges. Okay. We'll do one more here. So what if I had the sum as n equals 0 to infinity of 1 plus sine n divided by 10 to the n? Okay, well, let's look at the sequence part. 1 plus sine n divided by 10 to the n. Now, sine n will never be bigger than 1. It's never going to be less than -1 also, but it's never going to be bigger than 1, no matter what n is. So 1 plus 1 is 2. And, you know, the right side is always going to be greater than or equal to the left side. That will always happen because, you know, sine of n will never be bigger than 1. Okay? So this statement is going to be true for all n greater than or equal to 0. And let's see, if I look at the series given by the sum as n equals 0 to infinity of 2 divided by, or 2 times 1 divided by n, or 1 divided by 10 to the n, that would be a geometric series, which I know converges, right? Because the r value is less than 1 and bigger than -1, right? So I could find out what this series converges to. I don't need to know that though. All I need to know is that it converges. And I'm comparing, you know, something where all the terms are less than that. So if I add up, you know, all these smaller numbers, well, obviously I'm going to get something that still converges. Okay, so the sum as n equals 0 to infinity of 1 plus sine n divided by 10 to the n, that's going to converge also. Okay, let's go ahead and stop the video right here, and I'll show you some more of these in the next one, and then we'll also talk about the limit comparison test in the next video also.